before we introduce the speaker, the Joe will organize the dinner tonight if you want to join to talk after the seminar. So it's my great pleasure to introduce today's speaker, Thomas Nevins from UIUC. He will be talking about the Morse decomposition in symplectic algebraic geometry.
Thanks very much. Thanks very much for coming. Thanks for the invitation. It's great to be here. So I'm going to tell you some story about picture of Morse theory that occurs in algebraic geometry, and somehow maybe it's best to say sort of the Morse theoretic structures sort of inform the statements, but all of the kind of actual content is actually occurring purely algebraic. But I want to start out by just explaining some toy example. To kind of set the stage and sort of explain a little bit what's the motivation. Okay, so I'm interested in, so I'm going to start with complex n+1 space, and I'm always going to be interested in situations in which I have a group acting. So I'm just going to take the group of non-zero complex numbers acting here by rescaling. And somehow the setting for the talk is taking quotient spaces. So let me pretend that there are no algebraic geometers in the audience and kind of talk to you a little bit about how to take a quotient in algebraic geometry. So if I just take the orbit space here, and somehow the orbit structure is not very complicated, but there's a little bit of subtlety. So if I take a non-zero vector up to scaling, it's it determines a line, and the orbit just consists of all the non-zero points in that. So most orbits are free orbits; the group acts without fixed points, and most of the orbits sort of don't interact. But then there's this orbit at 0, which is in the closure of all other orbits. And so in particular, if I just take the orbit space in a kind of usual sense of a topological space, it's a non-Hausdorff space. So it couldn't possibly be an underlying algebraic variety. And so the question is somehow, what's the right kind of quotient to take in algebraic geometry to get something nicer? So what we do in algebraic geometry is we pass to some open set, semi-stable like this, and it's just picking some open subset where the orbit structure is nicer and we get a reasonable quotient. And in this case, I'm just going to remove that one kind of bad orbit. So now I really do have a nice Hausdorff quotient space. Now if I mod out by C star, I'm just taking lines through the origin. Really, each orbit is choosing an orbit is the same as choosing a line, and I just get complex projective M space as the quotient. Okay, so the procedure was sort of I pass to some slightly smaller open set, and then I have a reasonable quotient. Okay, so I'm going to refer to this as the geometric invariant theory or GIT approach. If I want to say this more scientifically, it's sort of determined by function theory. And the idea is just, well, okay, I look at algebraic functions, polynomial functions, on this space, and I ask somehow, is there a function that detects the existence of an orbit, detects sort of that it's alive? Well, okay, because I have this group C star acting, I should look only for certain kinds of functions that are well adapted to that thing, and the things that I'll look for are the homogeneous polynomials, the ones for which if I rescale, I get some power of that. Some power of lambda, rather than my scalar times the original function, so homogeneous polynomials. And then for a point of Cn+1, there's a homogeneous polynomial of positive degree that detects its existence, that takes a non-zero value at the point if and only if the point is not the origin. So I'm picking out exactly as this this locus of reasonable points sort of function theoretically the complement of the origin. Okay. There's a different point of view, which maybe I'll just write as Kahler point of view. But I also kind of secretly want to think of it as the Morse point of view on forming this quotient. And that's the following. Instead of sort of thinking purely in terms of this algebraic group acting on this algebraic variety, I could pass to a compact group. So pass to U1 now. So inside the group C star, I have a compact group, the circle acting. And I could pick a Hermitian form on this vector space, and that tells me a symplectic form. In this case, it's just a kind of constant symplectic form. A Kahler form, in particular. So let me write it this way, maybe. It's going to be a Kahler form. In this case, I can just take a constant form. And associated to that thing, there's some function to, well, in this case, just to the real line, if you like, but in general, it's to the dual of the Lie algebra. Okay. And in the example that I'm looking at, up to some scale conventions and so on, I should just be taking this function. And now, well, roughly what I want to say is I want to pick out a kind of nice subset of x using that function. So the kind of thing I could do is take the pre-image of some positive real number. So that'll be a subset of x. It's just a sphere. Let's see. 1 plus 1 sphere, if I'm counting correctly. And now I could mod that out by the compact group. Okay. So now I'm taking the sphere inside real 2n plus 2 space, and then I'm modding out by the rotation group. And again, I'll just hit Pn, Cpn. But alternatively, I could think of this as studying this function is sort of a little bit more Morse theoretically. So I'm using a particular value of the function to pick out a particular locus in this space by which I'm going to take a quotient. But instead I could sort of use sort of Morse theory of this function to break up my original space. So what I'm going to do is take, well, not really the function mu r, but really I'll take mu r minus c now. So I've shifted this thing. Well, okay, it's just a real value function at this point, but I could make sense of this in general. If I have something valued in a vector space, I could take the length squared of that thing if I pick an appropriate inner product on that target vector space. And, well, okay, so in my particular example, I'm just looking at, again, looking at this function, and now you can see what the critical locus is. It consists of that sphere together with the origin. And if I look at what points flow to under the downward gradient flow for this function, sort of the gradient flow breaks up Cn plus 1 into, well, everything except the origin. That's all the stuff that flows under the downward gradient flow to this sphere. And then the other subset is just the sphere, which is a critical point, so it doesn't move anywhere. Okay, so I told you sort of two ways to break up this space into two pieces.
It might help to say that there's an S1 action and there's an R plus action. You put them together, it's actually that C star action.
Yeah, that's right. The circle action is the restriction of the C star, right? So,
but the gradient flow is the other part.
That's right. Sure. Okay, so I've broken up my space now, and breaking it up in this way gives me a reasonable way to take the quotient just by taking a piece of the space. Okay, but again, somehow the point of giving this description here, I gave a perfectly reasonable. Okay, well, I haven't said much, but I gave a description that fits purely within algebraic geometry of trying to pick out some open set in the space of which I can take the quotient. But the point is, it also has some description, sort of in terms of some kind of Morse theoretic picture, and that's how I want to think a little bit later. Okay. Okay. So let me give one more example of this procedure of taking a space with a group action and picking a nice subset where I can take a quotient. So this is I would say less of a toy example. So here I'm going to take the group to be GLN, C, and it's going to act on the space consisting of pairs of an n by n matrix and an n-dimensional vector. Okay, so there's sort of only one, if you think about it for a little bit, there's only one action you can imagine doing. And that's that I conjugate the n by n matrix by the invertible n by n matrix, and then multiply the vector. So that's sort of the only natural thing I can do. Okay, well, I didn't say this before, but somehow you can imagine that maybe if you're used to Morse theory, that somehow there was some choice involved before. Maybe I said a little bit somehow. I didn't quite emphasize. I mean, there's a choice involved. I mean, somehow, if you're doing Morse theory, you're used to the idea that there's a choice of a Morse function, and things depend on that. Okay, well, I have to make some reasonable choice. I'm not going to tell you how I make that choice, but I have to make some reasonable choice of kind of Morse theoretic information in order to pick out a particular open subset that's nice for the quotient. But here, a kind of reasonable choice gives me this semi-stable open set. It consists of pairs with the following property. So I is an n-dimensional vector. I can take arbitrary polynomial expressions in the n by n matrix X. Let me write it this way. Multiply those by I. Each of those outputs is another n-dimensional vector. And if I take all possible polynomial expressions in X times I, that's a subspace. Okay? And now I want this thing. So it sits inside, it's a subspace of Cn because everything's taking place inside that, n-dimensional vectors. I want this thing to be n-dimensional. So I want it to really fill out the whole space. In other words, the way an algebraist would say this is I is a cyclic vector. For X. Okay, so I want to try to tell you some more Morse theoretic story about this. And in general, somehow, the details of kind of thinking in terms of Morse theory aren't really important. And in some sense, the details of picking out this particular subset aren't really important. The main principle is just that there's some scientific way of picking out open subsets for which one can take a nice quotient, and they're closely tied to Morse theory in some way. Now, in this case, I can also tell you what the quotient is. And maybe it's worth doing just because it's a kind of linear algebra. In fact, maybe there are two ways to say it. One is that I can think of it as the quotient of Cn by the symmetric group on n letters, but of course that's the same just as Cn itself. But the relationship is, I take a pair like this, and I just remember the unordered list of eigenvalues of the matrix X. Okay. So the point is just, so that's my identification with this set, and then of course such unordered n-tuples are given by coefficients of the characteristic polynomial of that polynomial. And so I get an identification with Cn again. The relationship is just that given an unordered n-tuple that I want to think of as eigenvalues of a matrix, there's the companion matrix associated to the characteristic polynomial, if you like. And that has the property that there is a vector like this. Okay? And in fact, the orbit of the pair is unique. So there's a unique orbit containing a matrix like that, containing that companion matrix and some cyclic vector for it. So that's the relationship between the original space and the quotient. So maybe it's worth just writing this. The relationship going back is companion matrix. Okay, so there's a basic question that this somehow, well, maybe it's first just worth saying, just pointing out that somehow many of the algebraic varieties that we're interested in come to us as quotients in this way. So typically, if we're interested in moduli spaces, parameter spaces of anything, they come to us as quotients. So somehow it's natural to build them, to construct them in this fashion. And so a kind of basic question you would ask, somehow, you might like to understand completely the geometry of that quotient space. A first question you could ask is, what's the cohomology of that quotient space? Okay, and let me just, as a convention, so that I don't have to write it anymore, throughout the top I'll just take complex coefficients. Okay, torsion, passing to the rational numbers wouldn't be a big deal. Passing to, passing to integral coefficients would be a problem. And torsion really would be a problem for the story that I'm telling. So I won't try to say anything about that. Okay, so the basic question is to compute the cohomology. Now, the two examples that I gave of the outputs of this, one is n-dimensional, a 2 n-dimensional real Euclidean space, so that's pretty easy to understand, and the other one is projective n-space. So in neither of these examples is the output something where I really need a theory to calculate. But in general, I do need a theory. In general, the output of this procedure, even starting from some relatively uncomplicated input, can be very complicated. So I'll say a little bit more about some specific examples later that we haven't quite touched on the construction, but I will shortly, where the cohomology is very complicated and interesting. Okay, so there's a sort of basic maneuver now. Which is useful in the general situation where somehow you have maybe no handle on this variety that you constructed concretely. The basic maneuver is to sort of try to use the cohomology of X itself. But of course, I really want the cohomology of the quotient, so what I'll try to think about is the equivariant cohomology of X to understand the cohomology of this quotient. Okay, so again, another kind of, so I sort of used, stated in a notational convention that I'm only interested in cohomology with complex coefficients. Let me make a standing assumption for the rest of the talk that G acts freely on this open set here, and just sort of further fix maybe standing assumptions. Standing assumptions is better. G acts freely on this open set, so that quotient will really be a nice, smooth algebraic variety. That's what I really want. And the other thing is that I want this group to be sufficiently nice, so I'm going to assume that it's complex reductive. So in particular, it's the complexification of its maximal compact subgroup. That was sort of implicit in what I was doing before in passing to Morse theory. I want to take a compact subgroup that really sees everything that the group G does in some sense. At least from a topological point of view. Oops, sorry. Reductive. If you're not happy with that terminology, you can just think product of general linear groups of various sizes. Okay, so the sort of implementation of the basic maneuver There's a lot of history here. I'm not going to try to give a anything like a detailed account. Let me mention just a few names. Atiyah-Bott, Kemp and Mess, Kirwan. And there are kind of important conceptual precursors, and there's a massive amount of much very important work following on these, but there was work right around very late 70s and early 80s doing just what I'm about to tell you, so let me explain that. So the implementation is to refine this decomposition that I wrote before. So before I wrote an open set inside X together with, there's a closed complement. I broke the space into two pieces before, but I sort of explained that I wanted you to think in terms of using a Morse function to kind of break up the space into those two pieces. Well, now in general, if I have a Morse function, there could be a lot of components to the critical locus, and I should look at everything that flows to each of those, and that'll break the space up in some more complicated way. So to a, kind of more refined Morse stratification, and let me just write X is disjoint union of some T gammas. And I won't tell you too much about what the labels are or anything like that, but it breaks, I just want to break the space up into some locally closed subsets in a nice way. But again, this has kind of interpretations both strictly in algebraic geometry and in Morse theory. So in Morse theory, it really is kind of Morse decomposition. I look at gradient flow down to certain critical loci, and I break the space up that way, where the Morse function I choose is the norm squared of a real moment map associated to a Kahler metric. Okay. So it's not really, there are subtleties here. It's not really a Morse function or a Morse-Bott function. It's a little bit worse than that, but this works. There's a purely algebro-geometric approach as well, and that's where I'm going to name the thing according to that and call it a Kirwan-Ness stratification. There's precedent in the literature. This is sort of precedented in the literature. It's not completely universal terminology, but there's a lot of history to the construction of such stratifications in algebraic geometry. I think, people might say it goes back to Hilbert, actually, in some sense. There's something called the Hilbert-Mumford criterion, which was proven by Mumford, but somehow he attributes the basic idea to Hilbert, and that Hilbert-Mumford criterion is sort of the seed of this method of stratifications. Let me just explain. So in the case of Cn plus 1 with this scaling action, I already told you everything, because I told you the two pieces. There was the semi-stable locus, and there's only one other point, so somehow there's no opportunity to stratify further. Okay. This semi-stable locus will always be the open piece of this stratification. And the point is this refinement is going to take the rest of the thing and break it up further. So in this example of GLN cross Cn, the T betas, or T gammas, it maybe makes more sense to call them TKs now, are the set of pairs x comma I, where now instead of asking for this vector I to be cyclic, in other words, the dimension of this subspace that I get by hitting I by all polynomial expressions in the n-band matrix X, instead of asking that to have full dimension n, I'll just ask for it to have some fixed dimension k. Okay, so I've written down now a bunch of strata, one for each number between 0 and n. So you can see I've just refined that part where the vector's not cyclic. I've broken it up further by sort of how far from being cyclic it is. Okay, and then the basic theorem in this subject then that makes this a useful way of attacking this this cohomological question is that the equivariant cohomology of X is the direct sum of the equivariant cohomologies of these pieces. Okay, each of these pieces is stable, is preserved by G, so I can ask, so it's now a G space, and I can ask for its equivariant cohomology. And the point is now somehow the Morse inequalities taken in the equivariant sense for this stratification actually become Morse equalities. So the terminology that people often use is, this is called the sort of equivariant perfection of Morse theory, where the space is equivariantly perfect. There's some geometry behind this. I mean, essentially the idea is that sort of if one works equivariantly, one has additional information in this stratification that you don't just have kind of in the fact that you broke the space up into these pieces. That additional information is that you can look at the group action on the normal spaces to these strata, if you're careful about how you say what you want. And in particular, now you write down the Giesen sequence in cohomology associated to the inclusion of a stratum, and you see that because of the way you've constructed this stratification, somehow the normal bundle is sort of, in an equivariant sense, is kind of highly non-degenerate. And it splits the Giesen sequence for you. So it just splits the cohomology of these pieces. Okay, so in particular, you get a surjection onto equivariant cohomology of the top piece. And again, by my assumption that this action is free, it's just the cohomology of this function. Okay, and that's a ring map. Okay, so now the approach is you could try to take that ring map and calculate the kernel of it. And if you can manage to calculate the kernel, you've on the nose determined the cohomology of this thing. And the idea is that hopefully this thing is simpler. And that's what tends to happen in examples that somehow, I mean, I wrote some quite trivial examples on the board, but somehow you can already see it in those examples. I started with Euclidean space. And I'm telling you that I'm getting a surjective map from equivariant cohomology to Euclidean space. So it's equivariant cohomology of a point, which is the kind of thing that was known to the giants of olden times. Okay, so I'm surjecting onto cohomology of projective space. Again, that's not so hard. In this other, the second example, again, the starting point was a Euclidean space. So again, the space is equivariantly contractible. Okay, and that tends to happen in examples. Somehow you often start from an equivariantly contractible space and build some very interesting space as a quotient. And this gives a good way to calculate. Okay, so the talk is billed as algebraic symplectic geometry. And so I want to do something sort of, if anything, more interesting. So there's a richer setting for building spaces. Well, whether it's richer depends on your point of view, but you get many more examples if you're willing to do a little bit more complicated construction. And that is to replace x by the cotangent bundle of x. Okay? If the group acted on, maybe I should start by writing just this. I have a group acting on x, I now get an induced action of the group on the cotangent bundle of x. Okay. Alright, so just as I was sort of explaining in this Kahler situation, there's now a function from that cotangent bundle that takes the values in the dual of the Lie algebra, moment map. Now it's not the same one as before. Okay, so there's the moment map. It takes values in the dual of the Lie algebra. It's just a thing that you get as follows. You have G acting on X. It tells you a homomorphism from the Lie algebra of G. If you differentiate the action to vector fields on X, you just dualize that and you get this map.
So you're doing it in the context where X is a complex manifold.
Yeah, still a complex
holomorphic form and a holomorphic moment map.
Yeah, that's right. I mean, so X is still a complex, smooth complex variety, algebraic variety. Cotangent bundle has a canonical algebraic 2 form. And, but there's a canonical moment map that you can write down without knowing that, right? Which is just this thing I said, dualize the infinitesimal action. So for example, in this case where I had GLN acting on this thing, now the cotangent bundle is, well, okay, is isomorphic to, it's just a vector space, right? So I take the dual cotangent bundle of that. It's the vector space cross its dual. Let me write it this way. GLN, n by n matrices are the same as their dual, even equivariant. So I have two n by n matrices, a vector and a covector, or a column and row vector. And now the moment map, if you calculate it in this situation, takes that quadruple to commutator of x and y plus ij. So it's just it's a calculation. Okay, so it's something quite linear algebraic. The thing to notice is just that you can sort of see, you would expect from this equation, this thing is typically quite, so I haven't finished saying the construction, so now the construction is of a space, maybe it's better to call it, well, Q for quotient. And the thing I'm going to do is, I'm going to take the zero free image of this map. I'm going to take this open set, the semi-stable locus, of which I can take a nice quotient, and I'm going to take the quotient of that thing. And that's a sort of complex algebraic Hamiltonian reduction. So it's a richer source of varieties. Of algebraic varieties. Okay. And things that arise this way here are some examples. Quiver varieties. In particular, ALE4 manifolds. This is probably familiar examples probably to many people. Moduli spaces of Higgs bundles. On curve. Many more interesting examples. But if you have any familiarity with any of these things somehow, the cohomology of these spaces can be very complicated and hard to understand. Let me point out, though, there's some complication already arising. And that complication is, unlike before, I've started with a singular algebraic variety. Okay? Even if I'm ending up with something that's smooth, this mu c inverse of 0 is usually singular. Okay, let me not be precise about, I mean, usually just means in most interesting examples, it turns out to be singular. Look at our example here. You can see I've written down, roughly speaking, some collection of quadrics. Okay, so it's an intersection of quadrics that I'm writing down or something. So that's going to have possibly many singularities, you would expect. And in fact, this particular thing, in this example, mu c inverse of 0 has n plus 1 irreducible components. Okay, so it's not just singular somehow, it's, it looks like it's glued together from kind of many independent algebraic varieties. Okay, each of which also typically happens to be singular, so it's somehow, it's a complicated thing. And I'm picking out one piece of that and taking the quotient of it. Okay, and I end up with some interesting space. But now there's a problem, so this is the hyperkahler Kirwan problem. And it's as follows. Stratify this variety Okay? It inherits a stratification from the cotangent bundle. Okay. Question now. So let me write it as disjoint union of S betas. And then the question is the cohomology is the equivariant cohomology of this space isomorphic to the direct sum of equivariant cohomologies of the pieces? In particular, does this cohomology surject onto, well, maybe even better. I mean, you could ask a better question. Does the cohomology so here's first question. Second question, does the cohomology of the cotangent bundle of X, so that's sort of the ambient space, I cut down to this mu inverse of 0, and then I take the quotient. Does that thing surject onto the cohomology of this quotient? Okay, so that thing would be called the problem of hyperkahler Kirwan surjectivity. Okay.
So your Q is the same as hyperkahler quotient.
Yeah, sorry, that's right. Q is that's right. Oh, sorry. Yeah, right. The point is right. So why is it called hyperkahler Kirwan surjectivity? Right, because if the original thing was hyperkahler, it's the hyperkahler quotient.
But you're not assuming that there actually is a hyperkahler.
Yeah, I don't need that actually for the story that I'm telling. So somehow the point of bringing up Kahler and Morse was to sort of motivate this idea that there's this nice stratification. In the case of, right, so maybe now's the time to sort of motivate, to say a little bit more kind of context. In the case in which the cotangent bundle that I'm starting with has a hyperkahler metric, and it's common that you just start with the cotangent bundle of some vector space. Okay, some complex vector space. So that's a quaternionic vector space. It has a hyperkahler metric. Then I'm just asking, what is the cohomology of the hyperkahler quotient surjected onto by the equivariant cohomology of this Euclidean space? But the Euclidean space is just equivariant cohomology of the point, because you can just contract the Euclidean space down to the origin. Okay, so that's the setting. So that's why it's called this hyperkahler Kirwan problem. Now it's difficult to approach, I think. I mean, this is what I'm an algebraist. I'm not an analyst, but or differential geometer. But I think it's difficult to approach as a Morse theory problem. In fact, there's been some progress in attacking this kind of problem, but the problem was not resolved by Morse theory. And the reason, I think, as far as I understand it, the literature on subject, the reason is sort of clear, because you have to pass through this thing, this singular thing, right? So you're taking cohomology here, you're restricting to here, and then you're trying to pass to this subspace and take equivariant cohomology of that. But you're passing through this singular thing, and that's the thing about which you want to try to do this Morse theory. Okay, so Morse theory on a singular space, not that easy. Okay? And so it wasn't something that's resolved. Maybe it's worth just saying a little bit more in this one example to convince you that there's something richer here than the examples I already saw. So far I haven't told you I've told you kind of interesting constructions of not interesting examples, maybe, or something like that. So let's go back to this example where I have this thing acted on by GLN, just induced from the action here that I wrote down before. Okay, so now the stratification here is the disjoint union of quadruples, x, y, and j, like I wrote down before, with the property that I is a cyclic vector, but now the point is it should be a cyclic vector for x and y. Meaning if I take all non-commutative polynomials in these two matrices x and y, apply such an expression to I, get a new vector, I take all linear combinations of those things. I can ask what the dimension of that thing is. Breaking the set up by the dimensions of those subspaces stratifies this space, and those are these Kirwan strata. In particular, if I take mu inverse of 0 semi-stable, modulo G, so that's the stratum where this vector is cyclic, generates the whole space. Now if I take the 0 pre-image of the moment map, I'm almost saying that x and y commute. Okay? Not quite, but it turns out on that particular piece, it does imply that x and y commute. So now I've got a cyclic vector and a pair of commuting matrices. That's an object of commutative algebra. Okay? And so now I could take the set, okay, so I have two commuting matrices. I could take the eigenvalue pairs of those commuting matrices. I could simultaneously make them upper triangular, read off the pairs of eigenvalues. That's only well defined up to reordering. Okay, so I would have I would have C2n, n pairs of eigenvalues, modulo the symmetric group. But in fact, this thing carries a little bit more information, and it turns out to be something called the Hilbert scheme of n points on C2, a resolution of the singularities of this quotient. So it's some quite interesting space. It's already a procedure for constructing a resolution of singularities, which is in general a highly non-constructive, complicated thing to do. It produces an interesting space. It turns out that just like in my earlier examples, this is a space for which there are other ways to get your hands on the cohomology. But in general, there aren't better ways to get your hands on the cohomology than by attempting to solve this Morse theory problem. Okay, so now we're far enough into the talk that even though I tell you the slightly disappointing news, it's pointless to leave at this point. The slightly disappointing news is that I can't solve that problem, but I can sort of come close. Okay, so I need to do something a little more sophisticated. Okay, and what I'll tell you is that I can sort of almost solve it in general. I would consider it a kind of corrected version of the problem. Okay, but then in some cases it does actually tell you that this answer to the second problem there, this hyperkahler Kirwan surjectivity, the answer is yes, it's surjective. Okay, so the slightly corrected version is that I'm going to replace t star x. Well, no, look, t star x has the same topology as x, right? So I may as well just contract the cotangent bundle down to the 0 section. Okay, so it's the same as asking whether equivariant cohomology of x surjects. And the corrected version is I'm going to replace that by something. So here's a new space, consists of pairs g comma x, with the property that g is in the stabilizer of the point little x. Okay, and then the theorem is that, well, okay, now the group acts here, if you like the x on the side here, and the equivariant cohomology of this space, there's a kind of natural map to this cohomology of this hyperkahler quotient or Hamiltonian rejection, and that surjects always. So this thing is what people would call orbifold cohomology. So it's sort of a good interpretation of the statement is that if you're willing to replace ordinary cohomology by orbifold cohomology, it always surjects. And again, I don't need hyperkahler for that. It has nothing to do with hyperkahler. And so I've been telling you a story only about cotangent bundles, but there are other kinds of symplectic algebraic varieties and other kinds of hyperkahler manifolds with group actions, and I don't see any essential obstruction to extending the statement to that generality, but I haven't worked that out yet, so I don't.
But since this is stated in terms of the action on x and not on t star x, how would you generalize the statement for a symplectic?
Yeah, well, calculating, I can tell you, I mean, at some point I'll tell you in the last few minutes of the talk, I'll tell you a somehow the actual statement of the theorem that proves this. And then the point will just be that somehow, that I think I can more or less prove in complete generality, but I'm not 100% sure then how to actually calculate the sort of invariants that one would need to calculate in order to get these cohomologies. So somehow this is a consequence of something that's well, I'll say in a couple of minutes. Okay, so maybe it's just worth mentioning. I guess, yeah, I don't know if the talk is sort of going out to the world or not, but I'll say something that's not yet fully documented. We haven't. This isn't completely written up, but I don't see any. I think the arguments are in place. Rather than stating it as a theorem or corollary, let me just say that in many hyperkahler situations, well, I don't know. Okay, many is sort of, it depends on your notion of many. Now the hypotheses really matter. Somehow, before what I said, somehow the hypotheses are very weak in everything I've done so far. Now the hypotheses really start to matter. In many hyperkahler situations, this implies hyperkahler Kirwan surjectivity. Sort of the original statement that I just now erased. Okay, so it was the Algebraic cohomology of X rather than of this slightly more complicated piece. Okay, so I should say, so this uses a weight argument that was explained to us by Nick Proudfoot and Ben Webster. And this will hopefully before too long. So the theorem that I've been telling you is already was posted on the archive a while back, and this argument will hopefully be appearing in a new iteration of that paper. So I should attach their names to this conclusion because we wouldn't be able to run the argument without this input of their argument. So, but it really relies on hyperkahler and something more. But in particular, I mean, assuming there are no problems with anything that seems to be correct, it seems to prove this hyperkahler Kirwan surjectivity for quiver varieties, for all quiver varieties. Which, as far as I understand, far from being known before. Okay, so there's a slight cost to this kind of general version, which is that this thing can be more complicated to calculate than the domain of the original Kirwan map, which was just equivariant cohomology of T star X, which is, in many examples would just be a vector space or something like that. So the calculation's already known for decades. Some of this thing can be more complicated, but the answer is if you're willing to do some mixed Hodge theory, you can get rid of that complication a lot of the time. Okay. I should say that you should not expect, however, that we just haven't done enough work to prove that conclusion in general. It's not true in some situations involving moduli Higgs bundles. And there are deep reasons for that.
What's not true?
The surjectivity, our statement is true in that situation as well. This statement is true. But the original hyperkahler Kirwan surjectivity is known by example not to be true for moduli Higgs bundles. And yeah, if you want to understand the kind of deep, there's some deep interaction there between cohomology and additional structures, and Mark Vitalo is far more expert than I am in that subtlety, and you should just ask him about that. Okay, so in the remaining few minutes, I just want to tell you sort of where does the theorem come from? I mean, why does algebra? This is maybe not the right place to say it, but why does algebra triumph over analysis? Temporarily. It's maybe not completely. I mean, as I said, I mean, I'm far from expert in the kind of Morse theoretic aspects of these things, but the Morse theory of, even in this original case handled by Kirwan, just taking an open set and a smooth variety and modding out by group, if you treat that in terms of Kahler geometry, the Morse theory is, surprisingly complicated. Whereas the algebraic geometry is somehow much simpler. It's much more combinatorial. We can, I can tell you an algorithm for calculating everything in terms of combinatorics of weights. Okay, so it does the same calculation in some sense as the Morse theory, but somehow it's less so. So it's maybe not so surprising that algebra is maybe a little bit easier way to attack this kind of problem. Okay, so where does the solution actually come from? I think, so this is sort of, the kind of, the real theme of the story is that it's a consequence of some kind of categorical version of Morse decomposition. So what do I mean by that? So I'm going to associate some category to one of these varieties, and there's some very interesting geometry in that category that somehow you can more flexibly attack by sort of changing what object you're looking at, so to speak. So the category. So again, let me return to this situation where I've got a group, complex reductive group, acting on a smooth algebraic, complex algebraic variety. And to that, I want to associate the category of D-modules on X. Okay, so I have this group acting, and so I want to allow G equivariant D-modules on X. Okay, so I don't want to try to tell you what a D-module is. I think somehow the details would, if you're familiar with them, they would bore you, and if you're not familiar with them, you wouldn't want to know. But let me give you some small amount of the flavor. And the flavor is that, if X is Cn plus 1 with coordinates, Z0 up to Zn, then there's this ring, which is just partial differential operators with polynomial coefficients. Okay. It's a ring, and so I can look at the category of modules over that ring. There are many analysts and differential geometers and so on in the audience, and so of course you know that everything about differential operators is well defined, without using local coordinates. So you'd be unsurprised to find that it makes perfectly good sense to talk about these things without using coordinates and so on. It's just some intrinsic thing on an algebraic variety. Okay. But of course, maybe on an arbitrary variety I can use sheaves or something like that. It's not a big deal. Okay. Now there's this additional complication maybe of equivariance, which plays an important role at a certain stage, but let me not try to be too specific about it. But there's some additional condition on a D module that makes it an equivariant thing. It sort of roughly looks like asking for a system of linear differential equations to be invariant under the group, but that's not quite, as a system, but that's not quite the definition. In any case, let's not worry about the details. There's a notion of this. And maybe now the crucial point is that just as the G action on T star X tells us, with some choice, a Morse or Kirwan mass stratification. It also tells us a Morse decomposition of the category. Let's just say in words for a couple of minutes. So, just like in analysis, I can take one of these modules and I can think of it as actually living. So somehow you can naturally see, right? If I have something that partial differential operators with polynomial coefficients act on, in particular polynomials act on. So it really lives over the space whose function theory is that polynomial ring. In other words, it lives on affine n+1 space. Okay. Now I've added these additional variables, and so you should be thinking to yourself, there's some space that tells me that this module actually naturally lives geometrically on. Okay, now it's a non-commutative ring, so somehow making sense of that in an algebraic way is complicated and not really possible in a clean way. But, you know, every analyst in the audience knows that, you know, that when we study linear partial differential equations, we study them microlocally. We study them not just locally in space coordinates, but also locally in momenta, locally in cotangent coordinates. And you could do the same thing with modules over this ring. Okay, so they really naturally live geometrically on the cotangent bundle, just as the theory of pseudo-differential operators does, the theory of microlocal analysis does. Okay, so let me write in order to sort of emphasize that, let me write microlocal sheaves on T star x to mean P modules. Okay? So I just want to emphasize that these are some kind of algebraic gadgets, but they live on the cotangent bundle. Okay. And now, there's some piece of those which are the ones that live on a particular stratum. So let me write this Morse decomposition into strata. There's some piece of these that live on a particular stratum. There's sheaves that actually just live on that smaller stratum. And then there's a restriction. I can restrict attention to the complement of that stratum. So actually, maybe it would be better if I sort of write T star x minus strata below S beta. Okay. Strata below S beta, and then here minus strata less than or equal to beta. And the Morse decomposition says that, well, okay, first of all, there's a short exact sequence of categories like this. So there are things on some piece, some Morse stratum, and if I kill those, what I'm left with is what lives on higher strata. But now, the thing breaks up, there's some canonical gluing information. And the theorem is that the middle thing is glued from the ends. This is what people in appropriate parts of algebra or algebraic geometry or topology would call the colon. Okay? It's a kind of familiar thing if you're used to studying for sheaves or something like this. But it's a complete shock in some sense that it happens here. But in particular, then, you get a lot of structure on any linear invariants associated to the category. So given a category, there are various kinds of vector spaces and groups that you can associate to it. So a very familiar one to algebraic geometers and algebraists is algebraic K-theory. But there's a slightly more complicated one, maybe, or a slightly different one, which is Hochschild homology. And if you compute that for these categories, what you get are exactly these things. And the fact that this thing in the middle is glued in this strong sense from the ends tells you that in particular there's this surjection. Question?
What is 7 functor?
What is, which one?
The second functor.
This one. It's just restriction to a smaller open set. Okay, sorry. My picture is very complicated. Maybe if I just draw a picture.
I thought these two categories are the same.
Sorry?
From what you wrote here.
Oh, it's, let me draw a picture, okay? So here's S beta. Here's the union over gamma less than beta of S gamma. And then here is P star X minus union over gamma less than beta of S gamma. So what it's saying is that if I throw away this, then what I'm left with is this stratum and the higher ones. And I can systematically break off strata one by one. And the category in the middle is always glued together from these in it.
So it didn't see quite clear what the second one is.
Here. Oh, I see. Sorry, I drew over it. Okay, I apologize. Okay. Anyway, so the picture is that this Morse theory, this way of breaking up the space into these pieces, is exactly mirrored by a very strong gluing structure on these categories. Now I can return to cohomology by calculating a linear invariant of this category. And when I do the calculation, I exactly get this surjection in the theoretic that I told you. So I guess the one remaining question was, what happens in more general situations where this stuff doesn't make sense? The categories always make sense. This decomposition should always hold. I think the linear invariants always make sense. The target will always be the cohomology of this thing, but the domain thing is the thing where you were complaining, I don't know how to, well, you were saying I don't know how to make sense of that. And yeah, I don't have as clean a calculation in that case of what the thing is. I mean, there's some description, but it's not as, at the moment I don't know as transparent a description. But the belief is that it should be much simpler to calculate still than this thing. So it should still give us some handle on that. Okay, I'm over time, so.